Yeah, I've been saying that I just want to talk about your progress with chapter 18. Personally, for me, it kind of come out as a hard chapter, actually. Probably also because of dense schedule this week, but also because Penrose, as he is saying in that chapter, his purpose here is not to develop the full details of a special theory of relativity, and probably his purposes were in non-synchronity with mine purposes here. So I've been kind of watching a lot of videos, and actually my head is kind of exploded till the end of the week. So I feel a bit like mushy. I don't know, like I saw a lot of things, but they don't have like a really clear structure in my head currently. So I'm a little bit lost. Yeah, and talking about this chapter, I managed like only through the first three subsections, and that's all. So we kind of can talk about those today.
Sounds great.
Yeah, so if everyone agree with this, I think we can start. Or maybe someone has something to share, like maybe more. Meanwhile, I will share my screen. Screen. I've been trying to to make the screen recording, but my notebook cannot afford this. So I decided not to record the screen and just show it to you and record only the book and my hand. So it's kind of the only option I have currently.
I think it's worked pretty well so far.
Okay. Yeah, I just want to use like more materials today and to show like exercise solutions to you, and those will be on the screen, but they will not be recorded, and that's why it's kind of pity, because I cannot like preserve that in the video recording. But anyway, okay, let's start. I will not, like the same way it was with the previous meeting, I will not concentrate like on the details, so I will just like make we'll try to make like a small overview of the ideas contained in these subsections. So basically, in this first subsection, Euclidean and Minkowskian for space, Penrose starts with the intuition of us perceiving the Euclidean for space, and he talks about also like the complexification of it and going to the C2 space in terms of this like product of two complex planes. And he says that the intuition for it is pretty straightforward, but sometimes we have like really puzzling or like entertaining or maybe amazing and exotic structures in four dimensions. For example, like Clifford parallels and stuff is Hopf vibration there. But anyway, if we take a look at the like coordinates and coordinate representation of the four-dimensional Euclidean space, then we will have just regular distance like this one. So we will have the similar 4 numbers to describe vectors there, and distance between 2 vectors will be calculated by the Pythagorean relation. Yeah, and basically if we formally define the difference as these variables here, like dx, dy, dz, then we can find that just rewrite this Pythagorean relation into this equation. Yeah, and if we move to the Minkowskian space, Minkowski spacetime, the only difference will be we should change our matrix, and its signature will change. We have 2 variants for the signature. It's like 3 pluses, 1 minus, and 1 plus 3 minuses signatures. And we have those corresponding equations here for those. And basically, the first one is positive for the distances, and therefore it kind of measures the space-like things, or as Chris calls it in his videos, it's probably something like absolute length or something like that, or proper length, probably maybe proper length. If we use this matrix, it will be positive for time-like things, and will measure the proper time actually. So it will be equal to 0 if you will travel with the light speed over the photon-like word lines in the Minkowskian spacetime. Okay, we have some pictures here, just like to differ between the null-like vectors, time-like, and space-like vectors. So basically, space-like vector lies outside of the cone, time-like lies inside of it, and null-like lies on the edge of the light cone. Yeah, as I have said already, ds will be equal to 0 for the photons, and now the question which Penrose give us is like, is that Minkowskian spacetime could be somehow similar to the E4 space? And he says that at the beginning of the special relativity theory, there was a tool or a way of making it into E4 space by using this relation, making the time a purely imaginary value. And that will make our dl squared or ds squared matrix the real ones, sorry, not only the real ones, but the same. They will turn. Okay, it will turn this DL metric if you substitute the IDV equation here into the regular ds squared matrix for the Euclidean space. But he says that this approach is not so good, especially if you will use it as a cornerstone for your theory. And he says that it's like this approach is used in what is called Euclidean quantum field theories currently, and he really doesn't like it because it kind of messes up, like mixing up the real coordinates and like time coordinate with the space coordinate too much. I'm not sure what he means exactly here, but probably he'll talk more about this in the chapter 28. Anyway, Penrose advises to use more complex approach, and he kind of complexifying everything. He advises just to replace all the coordinates we have with the complex numbers, and to use complex C4 space as a complexification of the E4 space, and therefore we will be able to obtain our E4 space, our Minkowski space with different metrics as the real subsections of the C4 space. And to do it, he advises to use the complex conjugation operation, and actually that's the first exercise given in this chapter. Kind of deduce how complex conjugation should act on the vectors in C4 space or CE4 space to kind of leave invariant the corresponding subspaces E4, M, and M with the wave. Basically, M and M with the wave are two Minkowski spaces with different signatured metrics. Yeah, and this approach kind of has like flat complex matrix CG there. So if we had the like regular Euclidean matrix in E4, then we will obtain the complexified G matrix in C4 there. And he kind of draws it in this picture as far as he can do it, because it's kind of impossible to imagine. So it's just a sketch of the like mental model for that, like having a big space and slices inside of it to depict our subspaces. Yeah, probably it's a good time to take a look at the first exercise. So basically, first exercise is talking about those complex conjugations, and we can define by taking the four vectors with the complex numbers, for example, the operation of complex conjugation of every coordinate there, or for example, conjugating every coordinate with putting a minus here, and like dually, we could have three minuses for like here. And basically, our four subspaces will be defined as the subspaces of C4, which will be preserved by such transformations. And for example, lambda, which is an element of E4, will be preserved by the C4 operation or the complex conjugation of all four coordinates, because all of those are real, right? And actually, the guy who wrote this solution, he kind of just swapped the M and M with wave. He just confused between those two. But it kind of doesn't matter here. Therefore, if we will have like three real coordinates here, then they will be preserved, and this one should be kind of complex one, like purely imaginary one, and therefore it will be preserved by this operation. And we kind of go into this representation Penrose mentioned at the beginning. Here, one moment, like probably like to this one. Yeah, so that's all for the first subsection. Maybe some questions.
Hello.
Yeah, hi.
Hi. I had a problem with the internet connection, but finally I got here. I have a question. I've been pondering about the length of the when you calculate the length in the dimensions. Is it really so that it doesn't matter how many dimensions you have? You can just take the square of the x, y, z, and so on. And then square roots, and it's always the length, and it doesn't really depend on the dimension.
Yeah.
You can take as many as you want. So that was one thing, and it was surprising for me So I just wanted to make it sure. So it doesn't really depend on if it's 4 or 5 or 6 dimensions, but it's the same.
Yeah, yeah.
The same algorithm.
But that will work only if you will use the orthogonal basis for the space. So in general case, you should have a metric here, and basically for the orthonormal basis, you will have all ones, like in this ds squared here. So you have 4 ones. But in Minkowski space, you will have like 1 minus, for example, here, or 3 minuses. But those are not like all variants. This space could have like different non-orthonormal bases, which will look like something like this. I'm kind of trying to show you my fingers. And if that basis will not be orthonormal, then you will have non-diagonal metric tensor in that basis, and therefore this formula could differ. So basically it will be like this. It's a more general case, like GAB, DXA, DXB.
All right.
And yeah, I suggest you to take a look at the video of Chris on YouTube. He has nice examples for the metric tensors.
All right. Yeah. And with a different sign, with T property, it has the different sign. But does it really make the difference that in space time the time is going only forward, not backward, only forward? Is it because of the sign, or is this sign more general thing? It just makes time different than all the other spatial dimensions, or does it depend to the direction of the arrow of the time?
Yeah, basically for the light word lines, if you take this matrix, for example, or that, you will have 0 for both of those. And basically, if you had like the same sign here, you kind of wasn't able to compensate like time changes in time with changes in distance. So therefore, it kind of corresponds to the like really connection of space to time, a kind of cocktail of space and time. It seems to me like that. So this change in sign here, it kind of allows us to mix time and space.
But it doesn't directly depend with the arrow of time, or does it? Does it have any relation to the arrow of time?
Arrow of time is kind of the direction of time.
I think time is always flowing forward. Doesn't matter if you put the negative sign in front of the t or the negative sign in front of the x, y, z. Just different conventions. I think that the physics works the exact same either way. You just have to pick one convention and stick with it.
Okay, so probably we should move on to the second subsection. And this second one talks about the symmetries of Minkowski space. And basically it starts with E4 symmetries and talks about like the symmetries of E4 are like translational symmetries, which are 4-dimensional symmetry group of translations, and also 6-dimensional rotation group O4, which kind of keeps the origin fixed and preserves the matrix. And if afterwards Penrose just complexifies the space and goes to CE4 here, and he says that we get a 10 complex dimensional group in that case of the symmetries of CE4 space. it's not obvious to me why it preserves metric, and he says also, like, moreover, all continuous motions of C4 to itself, which preserve the compactified matrix, are of this nature. And basically, he gives this as an exercise. And after reading that, I had like a few questions, like why is it so, and why the dimensionality will be preserved, and why we can just substitute the complex numbers instead of real ones and obtain the nice like formed symmetries in the complex space. But to understand it, we should read a bit further and kind of solve the next exercise. So in the next paragraph, he talks about, once again, about real slices of the C4 space and their symmetries. And he says that it would be really plausible that the groups which will correspond to the symmetries of those real slices will have the same dimension, namely 10. And to understand this, he kind of talks about that in Minkowskian case, we will have this Minkowskian Lorentz metric, and corresponding Lorentz group O31 or O13, which will preserve this metric. And the most general way to see that this Lorentz group of transformations is six-dimensional is to take a look at the Lie algebra of it and to check if that's true, actually. And that's exactly the case for the exercise number 3, which says, like, confirm it in the case of examining the 4/4 Lie algebra matrices explicitly. Yeah, and if we go to the exercise, sorry, one moment, browser is loading. Okay, and while it's loading, I had a bit of delay in the video also. Oh, sorry. My notebook doesn't feel well for some reason. I'm not sure why. And do you hear me well? Just the screen?
Yes, I can hear.
Okay, strange. Okay, for some reason my browser got kind of stuck, so I will talk a bit more on this subsection and afterwards we will continue. Basically, if we believe that the symmetries of those real slices have, the group of symmetries has the dimension of 6, then the full symmetry group of Minkowski space, including translations, 4-dimensional translations, will constitute the Poincaré group in recognition of Henri Poincaré. Yeah, that group is really important, especially in relativistic physics and particle physics and quantum field theory, because it turns out that according to the rules of quantum mechanics, individual particles correspond to the representations of the Poincare group, where the values for the mass and spin determine the particular representations. And at the end of this paragraph, Penrose talks more about the relativity principle for the special theory of relativity, and he says that for Minkowski space the relativity principle holds in first place because we can have those translations, and therefore every point of space-time is on the equal footing. And in addition, we have the spatial rotation symmetry, which will take 3 dimensions more, and that kind of sums up to 7 dimensions. And this leaves us with 3 more dimensions to express the fact that there is complete freedom to move from one velocity to another, and the whole structure remains the same, which basically M's relativity principle. And he says that more formally, what relativity principle asserts is that Poincare group acts transitively on the bundle of future time-like directions of M. And that phrase is kind of confusing, so I read a little bit on the forum about it, and the guys there talk that basically if we imagine that our Minkowski space is a base space, and we will form a tangent bundle there, each point of which is actually a point of Minkowski space and associated velocity, then Poincare group will act on these on that bundle nicely, and probably transitively. It means just shift every point with the associated velocity will be equal to any of such point transitively. So it seems intuitively to me it seems like that, but I'm still not on the firm ground with those bundle notions here. Yeah, maybe there was something else at the end. He also says that if we will preserve the family of simultaneity slices through the Galilean or Newtonian spacetime, then I don't understand what he's talking about. So he's saying that probably that will reduce the symmetry about a space-time point to these 3 dimensions without any freedom to move from one velocity to another. But probably I don't understand that also. So maybe someone has some thoughts about this theme, what does he means by kind of moving from one velocity to the other one here. Anyway, it's a good question, and probably need to write it somewhere, not to forget to answer that a little bit later.
I don't think I understand your question, Slava. What's the question?
Penrose here talks about that in Galilean relativity, we have only 3-dimensional symmetry about a space-time point.
Okay.
And therefore we will have no freedom to move from one velocity to another. And he says that if we move to the spatial relativity, we will have this freedom to move between velocities.
I think Because if you're dealing with 3D space, X, Y, Z, there's 3 different rotations you can do. You can do an XY rotation, YZ, and ZX rotations. But if you go to special relativity, you get 3 more, which are the Lorenz transformations. So Lorenz transformations are a bit like rotating in time and space. So you get TX, TY, and TZ rotations when you move to special relativity. And I don't think the equivalent of that exists in special relativity. I don't think you get those in Galilean relativity. Yeah. So it's only the space ones that you get.
Oh, okay. So it has to do with the commuting of the group elements, right? So it's like the Galilean boosts commute just fine, but Lorentz boosts, they don't commute. Like if you boost along X and then boost along Y, and then do an inverse boost along Y, and then inverse boost along X, I think you end up with a rotation.
Actually was not aware of that, so I don't know.
Yeah, I had a conversation with one of my professors about this a while ago. It's I believe this is called a Vigner rotation. Vigner rotation. And the idea is that because boosts do not commute, you end up with like a larger group for the Lorentz group as compared to like Galilean relativity forming a group. It actually doesn't. Let's see if I can find something. But yeah, the real deep conversation that I had with my professor about this was somehow the Vigner rotation is closely related to the Dirac equation and spinors somehow. I don't know. It's kind of mysterious to me, but somehow this non-commutativity of boosts is related to spin and spinners.
Yeah, I'm just looking at the Wikipedia article. I was not aware that Galilean boosts commuted, but Lorentz boosts did not. That's an interesting fact.
Yeah. Anyway, the example I wanted to show you, or exercise solution, opened at last, and therefore we've been talking about the Lie algebra for the like matrices who preserve the metric, and in our Lorentzian case, it will be O13 Lie group, and if its element will preserve the matrix, then this equation will be true. And basically, if we want to take a look at the Lie algebra, we can rewrite those elements using the infinitesimal element form and obtain this relation, and therefore after opening up the those brackets, we'll obtain GCD plus infinitesimal element with this equation in the brackets and some higher order terms that are with e squared or epsilon squared. And basically we're not interested in those, and GCD will just will be subtracted from the both sides, and we will be left with this thing, like the second part of it equal to 0, and therefore we'll obtain this equation which basically says to us that the product of the matrix with the algebra element is an antisymmetric matrix, and therefore a general solution X here of that equation will be our the algebra elements. And because we can like choose the right coordinate system in which we can set the matrix to this form with ones on the diagonal, and we can depict any antisymmetric matrix R components using 6 letters A, B, C, D, E, F. Therefore, we will be able to obtain the elements of the Lie algebra in this case, like those, just with some sign changes. And basically, because we have only 6 independent variables here to form the antisymmetrical matrix, we will have the exactly 6 elements of the basis for the Lie algebra. And basically, because the Lie algebra is kind of the tangent space for the Lie group, it will have the same dimension as the Lie group, and therefore our O13 group will be also 6-dimensional. Yeah, and if we will go back to the question like why we can complexify everything in the case of the E4 space and O4 group, then basically the argument on that forum was that it is because like the symmetries are like 2 symmetries, translational ones, which are 4-dimensional translations, which are obviously easily complexified because in C4 translations will be just translations by complex numbers. And the complexification of the Lie group O4 is actually like will be the same if we will use complex number instead of the real ones, and basically that's because of this process of like of calculation of the Lie algebra there, as far as I understand, and that means that it's kind of independent of the number system we will use here, like complex or real ones, and therefore we will obtain the same dimensions but with different numbers here, like complex one or real ones. And actually the overall form of those antisymmetric matrices will be preserved in the complex and real case, because those are exactly the matrices which corresponds to the infinitesimal elements of the Lie group, which will preserve the matrix like in our spaces. So like the basic argument goes like this, and that's the reason why we will obtain in each case after like complexification of E4 space and after taking those real slices, we will obtain the same dimension for the like 6, which will be equal to 6 for the all groups in different slices. Yep, so something like that. I'm not sure that I have understood the scene with velocities, which we have talked about here. Maybe we should discuss it on the next call also. Yeah, anyway, let's move to the third subsection. If you have any questions, please ask now concerning the second one. Yeah, we also had that picture with like a ball here and the cones and like hyperbolic sinks inside of it. Here, just to take a look like at different situations in E4 and in the Minkowskian space. Okay, so, and the next chapter, or subsection, will talk about like the orthogonality, and basically like the main idea here is that while complexifying the Euclidean space, we can kind of obtain non-standard notion of the orthogonality because now a direction can now be orthogonal to itself, which is something that certainly cannot happen in E4 space. And that feature persists when we going back to the like real sections like the Lorentz or Minkowskian space. And therefore, in this space-time, we will have this kind of strange notion of the orthogonality. And to consider it, Penrose goes to the notion of the orthogonal complement, which he depicts like this nu with a perpendicular sign here. And he defines this perpendicular complement operation for any nu, which is r-plane element at point P in space-time. And basically this orthogonal complement will be 4 minus r-plane element. And to obtain it, he says that we can use the index lowering procedure and kind of go between like dual R form and 4 minus R form by applying our matrix twice and lowering index twice, or making it go up twice. So this raise and lowering operation corresponds to passing to the orthogonal complement. And in E4, the orthogonal complement of 3 plane, for example, is a line element normal to this plane, like is depicted here. And for example, for a plane, two-dimensional plane, that will be two-dimensional plane also. And the directions between the nu and nu orthogonal will not be will not intersect actually, and we will obtain like independent directions in all of the cases there in E4 space. But if you will go to the different real section of C4, and in our case that's Minkowski space, in effect we will obtain the different situation, and in this situation, which can be seen more clearly from this picture here. On picture A we have Euclidean space, and in Euclidean space, if you have some vector and you will rotate it, then the orthogonal element will rotate the same way. It will go to the same direction. But in Minkowski space, if you have some vector and you will rotate it, then the orthogonal complement will come closer to it until the vector, as is depicted on the picture C here, will lie directly on the orthogonal complement to it. And as far as I understand, that basically happens because of the matrix we have chosen there. Here on this page, Penrose talks about that like the simultaneity, and this since he's been talking in the chapter 17 that we should abandon the absolute times there, and basically he been saying there that if we have like the absolute slices which we had in the Galilean space-time, I mean time slices there, then we will have, oh sorry, or I don't remember, probably I'm right. So we had this picture with time slices going through space-time. Yeah, and he said that then we can kind of take the complement, orthogonal complement there, and obtain like time slice is one-dimensional as far as I understand, and we will obtain three-plane orthogonal element Yeah, and basically he says that this, like, if we will have this time direction fixed, we will have some kind of special reference frame there, like the state of which he calls the state of rest. So basically he says that we will have this preferred state of rest there, with respect to which the speed of light will appear to be the same in all directions. Yeah, so I still don't understand that actually, like nicely, in a way to be able to explain it for you. Probably need to spend more time on this also. Okay, so he also said here that he will not develop the full details of the special theory of relativity, and I was kind of expecting and hoping that he will do so, because I kind of needed to be reminded and to kind of recall everything there. So at that moment I went to the YouTube and Chris's videos and watched everything in the relativity folder there. Still need to structure out it inside, like that material inside of my head. Okay, yeah, so here he talks that yes, he makes the point that the notion of simultaneity actually depends upon the observer's velocity, and that will kind of shift the simultaneity lines in the space-time. I saw something on the videos like connected with these things, but I'm not sure that I'm ready to comment about this like in a more detailed manner. Anyway, the ending of that subsection goes into the clock paradox, and basically, or twin paradox, which talks about like twins, probably one stays on Earth and the other one travels with big speed into the space and then comes back, and when he comes back he's still young and his twin is already pretty old on the Earth. And that fact is actually connected with the like stationary things for the like stationary passes, like on how we interpret the length in the space. In an Euclidean sense, we kind of always minimizing the length, this integral over ds here. But in the Minkowski space, for the time-like word lines, we're maximizing the proper time, and because of that, the triangle inequality will be like inverted in that case, and therefore like these paths from A, B to C will be, instead of being longer, will be shorter actually, and therefore because we are measuring the time here, we will have a shorter time here because the proper time is maximized over the straight word lines in the space-time. And you can see also here that there are some acceleration concerns in that case if you will have the triangle here, because kind of astronaut or twin will not be able to like stay alive after such a crucial change in accelerations, and therefore you kind of need to smooth out the angles there, but that will not change the situation drastically, and therefore the twin paradox will be still will be at place still. Yeah, and a small note at the end of this subsection is about that some people are saying that it's necessary to pass here to the general relativity, but in order we don't need general relativity while we are not taking into account the gravity questions. Yeah, so basically that's all for today in terms of the chapter. Maybe you have some questions?
Well, I have a comment about the sort of like principle of maximal aging that you were just talking about. So I think that's easiest to see from the invariance of the space-time interval, right? Like s squared is s prime squared, but if s squared is just the proper time squared, then any s prime will have a larger time because there is like a non-zero distance, right? A non-zero x component.
Yeah.
So if you just think of the invariance of the space-time interval, the principle of maximal aging is just saying that the time must be greatest in a frame where you know the two events happen at the same place. So that's how I think about the principle of maximal aging.
Yeah, true. So it's just like another form of talking about that integral over ds.
Right. Yeah. And so in the frame where you start and stop the clock at the same place, and you haven't moved, the proper time will be much greater than the time in a frame where you did move. And so you do have to do it as the integral, because you would do it infinitesimally, right? At each infinitesimal step, you'd have to preserve the interval.
Yeah, actually, like this week, I've been thinking also about the previous chapter, especially about the flat Minkowskian spacetime, and probably as far as I have understood, that the flat Minkowskian spacetime as a manifold, like it has the same tangent spaces at each points, which are isomorphic to each other, and actually are the same as Minkowskian flat space. So that's probably why we're kind of not using that manifold notation in special relativity, usually in like school or university books, as far as I understand. But Penrose kind of running up or running forward a bit, just to make it easier to transfer from that picture of flat space-time to the curved space-time, where we will have like more elaborate form for that form manifold, not a flat one.
So this idea of the tangent spaces looking the same everywhere, it's sort of a restatement of the idea that there's no preferred reference frame. Is that right?
Maybe I was thinking about like the Euclidean space to understand that like metaphorically or in comparison. So if you kind of take the plane element like this regular sheet of paper, then the tangent space at any point here will be the same plane, right? So they will be isomorphic, and the same if you will take a cube, then all cubes will be the same, and that's the exact situation as far as I understand it with the flat Minkowskian space. And it was really confusing for me because I always saw it like that, and only in chapter 17 Penrose been talking about those tangent spaces already while talking about the special relativity, and I was a bit confused last week because of that. And probably we can kind of use both point of views because they kind of equivalent ones. Okay, so if no questions, let's talk about plans. Probably. I have like a strong motivation to maybe structure like the material from the Chris's channel a bit, and maybe prepare something for the next call, for example, just to talk about the space-time diagrams and like the time dilations or length contractions, instead of going through chapter directly. Maybe that will be more effective thing to do. And for example, take like 1 or 2 sections only from the chapter for the next week. Just talk about hyperbolic geometry, for example.
I think it would be nice to see those diagrams. Do you have some geometry program you use for it?
What do you mean by program?
Like GeoGebra as an application that one can use for.
Are you talking about me like drawing something there?
Mm.
Yeah?
Yeah.
Probably I will not use that because I have camera and like those things.
Okay.
I will be more. It will be more comfortable for me, and will have like the shortest delay possible. Because I already tried to use the graphic tablets, but the delay was really big and not so useful or effective.
Well, anyway, it's a good idea.
Yeah, it'd be nice if I could find like it's like a web app online that lets you play around with Lorenz transformations, but I haven't seen anything like that. I'll post it if I find anything.
Yeah, actually, I just wanted maybe to show you a bit of like some frames from the quizzes videos, and basically like the best moments or something which I really liked. For example, while talking about the relativity principles, he was drawing like the frames like this, like the table about things we disagree on and the things we agree on, and basically with the relativity principle at the top, like the laws of motions are the same in all inertial reference frames, and in Galilean relativity we agree on the laws of motions and the gravity effects, but we will disagree on velocity, momentum, therefore momentum and kinetic energy, because basically the velocity will depend on like our point of view, our reference frame. And if you will move to the special relativity, we will have now like a little bit modified principle of relativity, where speed of light is the same in all inertial reference frames, and therefore we will not agree on the time changes and space or size changes, delta x and delta t here, but we will agree on the speed of light and on this space-time interval here, and also on the 4 vectors, which are like this space-time distance for velocity, for momentum, for acceleration, and for force. Yeah, what I also have here, for example, Yeah, I really liked his focus on the like three keys to the relativity, which are like invariance and covariance and contravariance principles. And basically, invariance is connected to the things like tensors, which are invariant for all observers, but could have like different representations in terms of components. And co and contravariance are about the kind of transformations of those invariant things, in which like one part will transform in contra way and other part will transform in the co-way, and basically like in the same direction, same proportion, and in exactly reverse proportion, and therefore the invariant will stay the same. And if you will form the Galilean relativity that way, we kind of can form for the Galilean space-time, we can form a basis for time, like a time ruler and space ruler, Et and Ex, and those rulers will change covariant, and the time itself and the distance, which will measure like the coordinates of our vectors in the space-time, they will change the other way, like contravariantly. And Galilean transformations, they could be represented also using the matrices, and that's kind of really easy to memorize. And if you multiply it, for example, if you multiply this matrix here on the Tx, you will obtain that like new T. We basically, by applying this transformation, we go in from this equation at the bottom. You can see like component change from T with wave and X with wave. To obtain those, we can just apply this matrix to the Tx, and basically it will preserve the time, because like time is still absolute there, and will change the coordinate, and coordinate will change depending on the velocity of our frame, reference frame. Yeah, and the same way, like the Galilean relativity can be represented using such transformations. We can also transform, use the same notions inside the special relativity, and we will have like more involved and more complex coefficients like gamma and betas are, and more sophisticated little bit matrices, but the principle will stay the same. So it kind of was really illuminating for me to see those there, and actually non-diagonality of that matrix is kind of what shows us that like the space and time will kind of will be mixed out. And yeah, probably that's all. Just wanted to share a bit of things with you, like a preview. Okay, so any questions?
I also sent one link to our chat channel. There are many great videos about special relativity and Lorenz transformation, but I found this very fantastic some months ago. There's a device that a person has invented that shows the transformation. It's quite cool. It's a series of videos actually.
Okay, I will take a look. I saw also that Pax sent the Zaskin's book here. I have it and I've tried to read it. I actually almost read everything about special relativity there, but it was far from perfect actually. Comparing to the Chris videos, it was really messy. Like a lot of things were really foggy for me and not so clear as Chris's videos. So I still recommend his channel as the main source of inspiration for special relativity, actually. Okay, so the basic plan is I will try to prepare like more answers to the questions we had accumulated for the previous two calls on the next call, and also maybe it's like some presentation of the special relativity notions based on the Chris's videos, and if we will have enough time, I will also write about hyperbolic geometry in Minkowski space, and maybe also about Riemannian sphere.